Good morning, everyone, and welcome to my presentation. Thanks to the organizers of this meeting for accepting my participation. I am Dr. Hmish from University of Béjaïa in Algeria. As you can see on the screen, our topic today is about thermal and structural analysis of extracted cellulose from olive husk. The purpose of this work is to extract this biopolymer from this waste. So think about it. Everything you eat, everything you wear, that comes from natural brown fibers or products. Indeed, natural fiber-based cellulose is primarily gaining attention as their application in advanced engineering materials is increasing. It has been estimated that there are a minimum of 1,000 forms of plants that produce gerbil fibers. Fibers are mostly extracted from different parts of plants, for example, cotton and capra from seeds, sisal and pineapple from the leaf. Just jute, flax, kenaf, rami, and hemp are obtained from the stem. Fiber and monocot genus from the fruit. Olive husk flour, as you can see here, is produced as waste during the olive milling process in olive producing countries. Large quantity of olive husk is realized into the wind or outright incinerated, induce so major nuisance to the environment. For this reason, it is pertinent to valorize and reuse this waste. For example, in Béjaïa produces, which is one town in the north of Algeria, the production is around 41,000 tons of olive husk per season. And the main constituents and chemical composition of olive husk are given in this table. Olive husk is composed of cellulose, hemicellulose, and lignin, and wax. And as you can see, the cellulose is the main component of olive husk. In order to extract the cellulose fiber, in this study, cellulose was extracted by chemical treatment, and it was characterized along with olive husk to compare the efficiency of the extracted cellulose for its various properties, presence or absence of hemicellulose, lignin, and thermal stability. So there are three steps. The first one consists of the purification of olive husk to obtain pure crystalline fractions from the pre-treatment of the selected natural fiber. Olive husks were first washed with distilled water several times, then dried. Fats, wax, and oil were removed from the skin powder sample by reflexing in a Saxley apparatus for 24 hours with acetone and ethanol. The second step consists in elimination of hemicellulose by using alkali treatment. It was treated with 3% by weight of sodium hydroxide solution at 80 degrees C in a water bath for 2 hours. After each treatment, the powder were filtered and washed with distilled water until the alkali was removed. The third and the last step is bleaching. To remove the lignin, the residue is bleached with a solution composed of equal parts of sodium chloride and acetate buffer. The bleaching treatment was performed at 120 degrees C for 2 hours under magnetic stirring and was repeated 4 times. After each treatment, the fibers were filtered and washed with distilled water. Like this, we obtained the cellulose from olive husk waste. After that, we proceed to the characterization of cellulose. The first characterization is the yield of cellulose, how much of cellulose is obtained from this waste according to this equation. The second characterization is FTIR. The AR spectra of olive husk, powder, and cellulose were analyzed with the Fourier transform infrared spectrometer. The equipment was operated with a resolution of 4 centimeter -1 and scanning range from 4,000 to 400. The third characteristic is the thermal behavior, and we use the thermogravimetry analysis, which carried out heating rate 10 degrees C per minute from room temperature to 20 degrees C. So the result obtained, we will start with yield of cellulose. As you can see here, after treatment process, we obtained 74% of cellulose was recovered. We also characterized the structural of the cellulose obtained. As we can see on this figure, the transmittance bands observed at 3040-20 and 2090-12. The spectra of olive husk fiber and the cellulose extracted were attributed to stretching vibrations of cellulose and CH groups respectively. However, after all treatments, the red spectrum is obtained. There are no more peaks showing the presence of lignin, hemicellulose, or pectin. Therefore, we can conclude that the elimination of lignin, hemicellulose, and pectin from olive husk is effectively done. So here we can say that after extraction, the FTR result confirmed that we eliminated the lignin and hemicellulose. There is only cellulose as a result. The second analysis is thermogravimetry, and the thermogram show that for olive husk there are 3 stages of thermal degradation. The first phase occurs in the range of between 70 and 100 degrees C. Is characteristic of the loss of water of the order of 77%. The second phase of thermal degradation arises around 285 due to the degradation of hemicellulose and the cellulose. The third one due to the degradation of lignin about 343 degrees C. So about extracted cellulose, 2 main mass losses. The first at about 100 degrees C is characteristic of the loss of water of the order of 5%. The second from 100 to 700 degrees C corresponding to degradation process of cellulose, such as depolymerization, dehydration, and decomposition of glycosyl units. This could be an indication of the elimination of hemicellulose, pectin, and lignin. As conclusions, we can say the FTR spectra show that there are no more peaks showing the presence of lignin, hemicellulose, and pectin. Therefore, we can conclude that the elimination of lignin, hemicellulose, and pectin from olive husk flour is effectively done, and the cellulose is certainly extracted. The second point is about thermal behavior. The thermogravimetric analysis revealed the degradation temperature of the extracted cellulose was higher than those of olive husk due to the high crystallinity of the cellulose compared to olive husk flour as waste. Finally, we can say the results confirm that the applied methods gives the high-grade quality of cellulose, which can be used as reinforcement in composite materials with biopolymer matrix. Thanks for your attention.